Possible causes of transformer failure can be broken down into several categories. Firstly, internal faults. Short circuits between turns in the windings or between windings and the core can lead to failures. Ground faults, which are faults between windings and the ground tank, are another potential issue. Also, loose connections resulting in poor electrical contact causing arcing and overheating. Secondly, thermal stress plays a significant role. Overloading the transformer by operating it beyond its rated capacity for extended periods creates thermal stress. Insufficient cooling, due to blocked airflow or inadequate oil circulation preventing heat dissipation, contributes to thermal stress. Aging insulation also degrades over time due to heat and oxidation. Thirdly, environmental factors can cause transformer failure. Moisture ingress into the transformer can lead to insulation breakdown. The accumulation of dust and contaminants can impair heat transfer and insulation properties. Lightning strikes can introduce surge voltages that damage windings and insulation. Fourthly, mechanical stress can be a factor. Abnormal vibrations from external sources or internal faults can cause mechanical stress. Impacts, which include physical damage to the transformer housing or windings, are another source of mechanical stress. Seismic activity, such as earthquakes or tremors, can cause structural damage to the transformer. Specific causes for the reported failures include zero resistance on the primary side. This could be due to an internal short circuit, where a short circuit between primary turns or between primary and secondary windings can cause the resistance to read zero. An explosion is often due to overpressurization, where excessive internal pressure stems from a severe fault or explosion of the insulating oil. Arc flash, which is a catastrophic electrical discharge within the transformer, resulting in violent expansion of gases, can also cause an explosion. Additional considerations include overvoltage from the utility. Even if overvoltage has been ruled out, verifying the voltage supply from the utility with a reliable source is still essential. The transformer's history, including previous maintenance records, operating conditions, and environmental factors, can provide insights into potential causes. A thorough inspection and diagnostic tests are crucial. An expert assessment of the damaged transformers is necessary to determine the exact cause of failure and recommend appropriate repairs or replacements. Internal faults in transformers can manifest in different ways. One type of internal fault is a short circuit. This can occur between the turns of a winding, effectively bypassing a portion of the winding and causing a large current to flow. Short circuits can also occur between different windings, such as between the primary and secondary windings. Another type of internal fault is a ground fault. This happens when a winding comes into contact with the grounded tank of the transformer. This can create a path for current to flow to ground, which can be dangerous and damaging. Loose connections within the transformer are another source of problems. Poor electrical contacted connections can lead to arcing and overheating, which can degrade insulation and eventually lead to failure. Thermal stress is a significant factor in transformer life. Overloading a transformer causes it to overheat, which accelerates the degradation of insulation. The rated capacity of a transformer is the maximum load it can handle continuously without exceeding its temperature limits. Insufficient cooling exacerbates the problem of overheating. Transformers rely on either air or oil circulation to dissipate heat. Blocked airflow or inadequate oil circulation can lead to higher temperatures and accelerated aging. Insulation materials degrade over time due to heat and oxidation. This degradation reduces the insulation's ability to withstand voltage stresses, making it more susceptible to failure. Environmental factors can also contribute to transformer failure. Moisture is a major enemy of insulation. It can penetrate the transformer and weaken the insulation, leading to breakdown and short circuits. Dust and other contaminants can accumulate on the transformer surfaces, impairing heat transfer and reducing the effectiveness of the insulation. Lightning strikes can generate very high surge voltages that can damage the transformer's windings and insulation. Surge arresters are often used to protect transformers from lightning strikes. Mechanical stress can also cause problems. Excessive vibrations can loosen connections and damage windings. Impacts or physical damage to the transformer housing can also compromise its integrity. Seismic activity can cause structural damage to the transformer, especially if it is not properly anchored. The specific issue of zero resistance on the primary side indicates a severe short circuit. A short circuit between primary turns or between primary and secondary windings can effectively create a very low resistance path, causing the resistance reading to be close to zero. The explosion is a serious event that can be caused by overpressurization or arc flash. Overpressurization can occur due to a severe fault that generates a large amount of heat, causing the insulating oil to vaporize and create excessive internal pressure. Arc flash is a catastrophic electrical discharge that can generate intense heat and pressure, leading to an explosion. When investigating transformer failures, it's important to verify the voltage supply from the utility to rule out overvoltage as a contributing factor. Overvoltage can stress the transformer's insulation and lead to failure. Reviewing the transformer's history, including maintenance records, operating conditions, and environmental factors, can provide valuable clues about the cause of the failure. A thorough inspection and diagnostic tests are essential for determining the exact cause of the failure. This should be performed by qualified experts who have the necessary knowledge and equipment. Diagnostic tests may include insulation resistance tests, turns ratio tests, and oil analysis. These tests can help to identify insulation degradation, short circuits, and other problems. Based on the findings of the inspection and tests, appropriate repairs or replacements can be recommended. Proper maintenance and monitoring can help to prevent transformer failures. This includes regular inspections, oil sampling, and infrared scanning to detect hotspots. Surge arresters should be properly installed and maintained to protect against lightning strikes. Transformers should be operated within their rated capacity to avoid overloading and overheating. Adequate cooling should be provided to ensure that the transformer does not exceed its temperature limits. Also consider the short circuit impedance of a transformer. The impedance limits the current that flows during a short circuit. If the impedance is too low, the short circuit current can be very high, which can damage the transformer. The impedance is usually expressed as a percentage of the transformer's rated voltage. For example, a transformer with an impedance of 5% will limit the short circuit current to 20 times the transformer's rated current. Core saturation is another factor to consider. When the magnetic core of a transformer is saturated, it can no longer effectively transfer energy from the primary winding to the secondary winding. This can lead to overheating and reduced efficiency. Core saturation can be caused by overvoltage or by operating the transformer at a frequency that is too low. Harmonics in the supply voltage can also cause problems for transformers. Harmonics are voltage or current waveforms that are multiples of the fundamental frequency. Harmonics can cause overheating, reduced efficiency, and increased noise. Harmonic filters can be used to reduce the level of harmonics in the supply voltage. The tap changer is a device that allows the voltage ratio of a transformer to be adjusted. Tap changes are used to compensate for voltage variations in the supply voltage or to adjust the output voltage of the transformer. Tap changes can be either manual or automatic. Oil quality is also an important factor for oil-filled transformers. The oil serves as both an insulator and a coolant. Over time, the oil can degrade due to contamination, oxidation, and thermal stress. Regular oil sampling and analysis can help to identify problems with the oil. The oil should be replaced or reconditioned when it becomes degraded. Bushings are used to connect the windings of a transformer to the external circuit. Bushings must be properly insulated to prevent flashovers. Bushings can be damaged by overvoltage, contamination, or mechanical stress. The cooling system is essential for preventing overheating. The cooling system can be either air-cooled or liquid-cooled. Air-cooled transformers rely on natural convection or forced air to dissipate heat. Liquid-cooled transformers use oil or other fluids to transfer heat away from the windings and core. The protection system is designed to protect the transformer from faults. The protection system typically includes fuses, circuit breakers, and relays. The protection system should be properly coordinated to ensure that it operates quickly and effectively to isolate faults. When a transformer fails, it is important to investigate the cause of the failure to prevent future failures. The investigation should include a review of the transformer's history, operating conditions, and maintenance records. The investigation should also include a thorough inspection of the transformer to identify any signs of damage or defects. Consider dissolved gas analysis. Dissolved gas analysis, or DGA, is a diagnostic test that can be used to detect incipient faults in oil-filled transformers. DGA involves analyzing the gases that are dissolved in the transformer oil. The presence of certain gases, such as hydrogen, methane, ethane, ethylene, and acetylene, can indicate specific types of faults. For example, high levels of hydrogen can indicate overheating, while high levels of acetylene can indicate arcing. DGA can be used to detect faults early, before they lead to catastrophic failure. Also consider frequency response analysis. Frequency response analysis, or FRA, is a diagnostic test that can be used to assess the mechanical integrity of transformer windings. FRA involves injecting a signal into the transformer and measuring the response. The response is then compared to a baseline measurement to identify any changes. Changes in the frequency response can indicate winding deformation, loosening of clamping structures, or other mechanical problems. FRA can be used to detect mechanical problems that may not be apparent from other tests. Partial discharge measurement is another option. Partial discharge, or PD, is a localized electrical discharge that occurs within the insulation of a transformer. PD can be caused by defects in the insulation such as voids, cracks, or contamination. PD can gradually degrade the insulation and eventually lead to failure. PD measurement involves detecting and measuring the PD activity within the transformer. PD measurement can be used to identify insulation defects and assess the condition of the insulation. Infrared thermography is also another option. Infrared thermography is a non-destructive testing technique that can be used to detect hotspots in transformers. Hotspots are areas of elevated temperature that can indicate problems such as loose connections, overloaded windings, or blocked cooling ducts. Infrared thermography involves using an infrared camera to scan the transformer and create a thermal image. The thermal image can then be analyzed to identify hotspots. Visual inspection should be done carefully. A careful visual inspection of the transformer can reveal many potential problems. The inspection should include checking for signs of oil leaks, corrosion, damaged bushings, and other defects. The inspection should also include checking the condition of the cooling system and the protection system. Review the maintenance records. A review of the transformer's maintenance records can provide valuable information about its past performance and any potential problems. The records should include information about oil sampling, DGA results, and any repairs or replacements that have been performed. Also consider the operating conditions. The operating conditions of the transformer can have a significant impact on its life. Overloading, overvoltage, and excessive harmonics can all accelerate the degradation of the transformer's insulation. The transformer should be operated within its rated capacity and voltage limits. Harmonic filters should be used to reduce the level of harmonics in the supply voltage. Also consider environmental factors. Environmental factors such as temperature, humidity, and pollution can also affect the life of the transformer. Transformers should be located in a well-ventilated area and protected from moisture and contaminants. The transformer's grounding system should be properly designed and maintained to prevent ground faults. Surge arresters should be properly installed and maintained to protect the transformer from lightning strikes and other voltage surges. Regular maintenance should be performed on the transformer to keep it in good condition. Maintenance should include oil sampling, DGA, visual inspection, and testing of the protection system. The results of the investigation should be documented in a report. The report should include a description of the failure, the cause of the failure, and recommendations for preventing future failures. Also, the condition of the core is important. The magnetic core of a transformer is responsible for channeling the magnetic flux that transfers energy between the primary and secondary windings. The core is typically made of laminated steel to reduce eddy current losses. Damage to the core, such as delamination or saturation, can significantly reduce the transformer's efficiency and increase its operating temperature. Winding insulation failure happens. The windings of a transformer are insulated to prevent short circuits between turns or between windings and the core. The insulation can be made of paper, varnish, or other materials. Over time, the insulation can degrade due to heat, moisture, and electrical stress. Insulation failure can lead to short circuits and catastrophic failure of the transformer. Tap changer problems can be due to mechanical wear and tear, electrical contact corrosion, or contamination. These problems can lead to incorrect voltage ratios, overheating, and eventual failure of the tap changer. Cooling system malfunctions can result from blocked cooling ducts, pump failures, or fan failures. These malfunctions can lead to overheating of the transformer, which can accelerate the degradation of the insulation and reduce the transformer's lifespan. Protection system failures can result from incorrect settings, faulty components, or lack of maintenance. These failures can prevent the protection system from operating properly in the event of a fault, which can lead to severe damage to the transformer. Partial discharge activity within the transformer can be a sign of insulation degradation or other problems. Monitoring partial discharge activity can help to detect problems early before they lead to failure. High oil temperature or oil contamination can indicate problems with the transformer's cooling system or internal insulation. Regular oil sampling and analysis can help to detect these problems. Winding deformation can result from short-circuit forces or mechanical stress. Winding deformation can reduce the transformer's ability to withstand short-circuit currents and can eventually lead to failure. Core insulation failure is also a concern. The core of a transformer is also insulated to prevent short circuits between the laminations. Failure of the core insulation can lead to increased eddy current losses and overheating. Lightning impulse test can verify the ability of a transformer to withstand voltage surges caused by lightning strikes. The test involves applying a high voltage impulse to the transformer and measuring the response. The transformer should be able to withstand the impulse without any damage or failure. Switching impulse test can verify the ability of a transformer to withstand voltage surges caused by switching operations. The test involves applying a high voltage switching impulse to the transformer and measuring the response. The transformer should be able to withstand the impulse without any damage or failure. Applied voltage test can verify the integrity of the transformer's insulation. The test involves applying a voltage higher than the rated voltage to the transformer and measuring the leakage current. The leakage current should be within acceptable limits. Induced voltage test can verify the integrity of the transformer's insulation at a higher frequency than the applied voltage test. The test involves applying a voltage at a higher frequency to the transformer and measuring the leakage current. The leakage current should be within acceptable limits. Turns ratio test can verify the accuracy of the transformer's turns ratio. The test involves measuring the voltage on the primary and secondary windings and calculating the turns ratio. The calculated turns ratio should match the nameplate turns ratio. Winding resistance test can measure the resistance of the transformer's windings. The resistance should be within acceptable limits and should be balanced between phases. Impedance test can measure the impedance of the transformer. The impedance is a measure of the transformer's opposition to the flow of alternating current. The impedance should be within acceptable limits. Frequency response analysis can assess the mechanical integrity of the transformer windings. The test involves injecting a signal into the transformer and measuring the response. The response is then compared to a baseline measurement to identify any changes. Insulation resistance test can measure the resistance of the transformer's insulation. The resistance should be very high, typically in the megaohms range. Polarization index test can assess the condition of the transformer's insulation. The test involves measuring the insulation resistance at two different times and calculating the polarization index. The polarization index should be within acceptable limits. Dissipation factor test can measure the dissipation factor of the transformer's insulation. The dissipation factor is a measure of the energy lost in the insulation. The dissipation factor should be within acceptable limits. Oil dielectric strength test can measure the dielectric strength of the transformer's oil. The dielectric strength is a measure of the oil's ability to withstand voltage stress. The dielectric strength should be within acceptable limits. Oil acidity test can measure the acidity of the transformer's oil. The acidity is a measure of the oil's degradation. The acidity should be within acceptable limits. Furan analysis can identify the presence of furans in the transformer's oil. Furans are byproducts of cellulose degradation and can indicate insulation degradation. DGA can detect incipient faults in oil-filled transformers.